Let us prove that the set of the real numbers is uncountable. So how are we going to do that? So what we are going to do first is to consider a subset okay, a subset S of the real numbers between 0 and 1 that have a very special decimal expansion, that have only zeros and ones on their decimal expansion. Okay. So these are going to be all numbers that will look like 0, 1, 1, 0, 0, and so on, because it's a set of the real numbers. We should expect that some of these decimal expansions will never end. Okay. So now we are going to show that S is uncountable. Okay. So proof is by contradiction. Assume to the contrary that S is countable. Okay. If it is countable, then we are going to be able to put all the numbers in S in an enumeration. We are going to be able to enumerate all members of S. Okay, notice that I underlined all the members of S. So let's suppose we have some enumeration. It doesn't really matter what particular enumeration we have. Okay, so let's say we start with all zeros. Let me put a few more. And then we have x2, x3, x4, and so on. Okay, then we have 0 dot 0, 1, 0, 1, 0, 1, 0 dot 0, no, 1, 1, 0, 1, 0, 1. Then we have 0, 0, 1, 0, 1, 1. As I said, it doesn't really matter what we choose. Okay, just the question here is that they don't repeat. Okay, it's just an enumeration. Here we can enumerate because we are assuming that the set is countable. Okay, and now this is what is called a Cantor diagonalization argument. This guy Cantor used this type of argument in the 19th century to show that the set of real numbers was uncountable. Okay, so now what we are going to do, we are going to construct a new number x. Okay, looking for the sequence, for the first number x1, I'm going to look at the first decimal position. For the second number, second position. Third number, third position. Fourth position. And so on. Okay, here the point, you see it's a diagonal. That's why it's called a diagonal argument. Here the point is that with this, we can construct another number that is 0.0100. You see what I'm doing? I'm just bringing these numbers, okay, these positions I highlighted. Okay, but this is not the number I want. The number I want is the negative, the opposite of this one, if you want. Opposite, not in the usual sense. What I'm going to do is I'm going to flip every position. So if it was 0 in the first position, now I write 1. If I had 1 in the second position, I write 0. 0, I write 1, 1, and so on. I always write for the position n. Okay. Take the opposite of the nth digit of xn. Okay, so this is the rule that defines x. And now here's the magic. This number x that I just defined cannot be in the sequence, in this sequence that enumerates all the members of S. Okay, let me actually say it properly. Then X is not in the enumeration of all members of S. Why is so? Because by construction, the nth digit of xn and x are always different. Okay, basically I have defined the number x so that the nth digit of xn is different, is the opposite. Okay, so this means because this enumeration contains all the elements of S, this means X doesn't belong to S, but X is clearly a member of S. Because of the definition of the set S. All right, the set of all numbers, real numbers that have only ones and zeros in their decimal expansion. So this is a contradiction. Therefore, S is uncountable. Okay, but we saw last week that whenever we have a subset of another set and the smaller one is uncountable. Okay, let's write it properly. Okay, so if we have that S is a subset of R and S is uncountable, then R is uncountable. Or in other words, we could say that if the larger set is countable, then the smaller must be countable too. Okay, so this is the proof that the set of the real numbers is uncountable.